So if I talk about the photoelectric effect, you can tell me what it is. Because so in other ways, if I say write the equation that describes photoelectric effect, can you write it down?
Yes.
You can write it down.
Yes.
So if you can write it down, it means you can also describe. If I put a plot, and in that plot I have on my ordinate I have my kinetic energy, and on the axis I have frequency, and then I draw a straight line. Can you already imagine how that straight line looks like? Can you describe, can you tell me what that straight line means? Because, if you understand, there is only way that straight line looks like. There is only one way. So, I have on the y-axis, as we would call it, my kinetic energy. So, that axis goes through zero. It extends across zero. And then on the horizontal at zero, I draw my frequency. And then I draw my frequency, and then I have a straight line.
So does the line crosses at the zero at the cross, or it cuts at the y, or cuts at the x, or
you know it. It's in the textbook. It's in the textbook. All I'm saying is that.
Okay.
All I'm saying is that you've got a straight line there. How it looks like, you already know, because it's in the textbook. In other words, I'm saying that equation that you say you can write it down, you can write down, has got to do with a diagram. A diagram that is in the textbook. That is why last time I said you cannot divorce equations from diagrams that are in the book, in the textbook. You take them in conjunction. Okay? So if you've got an equation and there's a diagram, you must understand what is it?
What's the relationship?
Yes. That you must know. That you must know. For instance, out of the diagram I'm describing to you, I can calculate Planck's constant. Can you do it? The gradient, yes. Can you?
Yes.
Good. If you can do that, fine. Now, can you explain to me what the Balmer series is? What is it? Talk. You have to talk.
Oh, you're asking for an answer right now. It's in the visible region.
What is the Balmer series? What is it?
It represents, if I'm not mistaken, those lines.
What are those lines? What?
It's in the visible region, and then I don't know what the lines are called, but they represent the image, like.
Line.
But you have
the line
spectra. Line spectra of what? Please, register. Please, complete the register. Then give the page. So, what line spectra? Line spectra. Continue.
The hydrogen in the visible region, and then.
In particular, hydrogen atom.
Yeah, hydrogen atom. Yes.
If you are saying hydrogenic, that's a general term. It can mean anything. It can mean uranium. You take the uranium atom, you remove all of it, so then you leave one. That's a hydrogenic atom. So, but when we talk about the Balmer series, we're talking about a specific element. That is hydrogen. That is hydrogen. So, now, what about hydrogen? How do you get the Bama series? You want me to repeat myself?
So the lines.
Use the formula.
No. Formula cannot give you those lines. How do they come about?
They measure when an electron moves.
Excited and then.
No, when it goes down. When it moves from a higher energy level to a lower.
Why does it move from a higher energy? I mean, in hydrogen, the electrons are in the s orbital. What were they doing there in the outer one?
Because they probably absorbed light.
How did that happen?
The light was.
Maybe exposing it to ultraviolet light or visible light. Visible radiation. Exposing it to light.
Okay. And then
the electrons get excited, and then and then the electron gets excited, and then after it goes down, goes back to the ground state.
Ground state?
Not ground state, because there are different levels. So those lines tell you about the different, what do you call it? energy difference. Energy level.
Energy level.
Yeah.
Which in particular? Which energy level in particular? Which energy level in particular? Which energy level in particular?
The one associated with the wavelengths and the visible region.
Which I'm asking about the energy level in the hydrogen atom. Which that is involved with the Bama series. Which energy level is that?
Energy level. Okay. I'm thinking it's from N2 and then onwards.
Please, be serious. We're talking about quantum numbers.
Yes.
We're talking about quantum numbers. So, if we're talking about energy levels in hydrogen, which quantum number are we talking about? The principal quantum number, N. So, my question is, which N? So what is the range of N at all? What is the lowest N you can have?
1.
It's 1. So, which N is it that is involved in the Bama series? That's my question.
2.
It's 2.
Yeah, 2.
That shouldn't be difficult.
Yeah, that's it.
That is part of information that should be in your fingertips or at your fingertips. It's 2. So, what happens is that if you have got, you know that atoms of hydrogen are highly reactive. They're highly reactive, so they don't just exist. So they must come from somewhere. So, stable hydrogen exists as a gas, and it's diatomic. So, if you take hydrogen gas, you put it in a spark. Must stop me as soon as I say something you don't understand. You put it in a spark, where there is electricity jumping from one point to another. The temperature is very high. There is a lot of energy there. It splits the atom. Splits the molecule into atoms. So it injects high energy into this molecule, and so highly energetic atoms result. And so these electrons, which formed the bond, are now in the single atom. Each one in the single atom. So what they do is they experience now the force of this nucleus, plus nucleus. And they descend now, passing through all these energy levels, and they can go even up to 1. That we call the alignment series. And if they go to n equals 2, we call that the Balmer series. And so on and so on. Why then now many? It's because they are coming from different energy levels, but they all end up at n equals to 2. So that group is called the Balmer series. Okay? So
it's the same hydrogen.
Say it again.
It's the same hydrogen. It goes through the lining, the passion, the bracket, and the fund.
We are talking about one electron.
No, but it's the different levels, right? So if it goes up, if it goes to 1, it becomes Lyman. If it goes to 2, it's Balmer's. If it goes to 3, it's passion.
Yes.
Okay.
But also, they can the starting point. Well, you can say that if the electron can leave the atom literally, but if it's not outside the atom, so it can start on any higher energy level and descend. Okay? So, even on higher energy levels, they start from different positions, from different energy levels. Okay? So, but those that go down right to the to n equals 1, that group is called the Lyman. And those that go, they end up at n equals to 2, they're called the Balmer series. So even in the spectra, you can see them. They are in groups. They're in groups. You can see that the Balmer series is here, the Lyman is here, and so on and so on. Okay? So you must ask you must interrogate yourself when you read any information you read in the textbook. Interrogate yourself. Try and imagine you telling it to somebody else. Trying to make someone else understand what you're talking about. So I hope you will go back and look at these lines and try and make sense of them. Yes. Okay? So angular momentum. What do you understand about angular momentum? This is the reason why I said to you, you need to read not just the prescribed textbook, but read all those recommended textbooks. And then write notes. Go there armed with a pen and a notebook and write down what that author is saying regarding this topic. What are they saying regarding this topic? And then you will collate all that information. I mean, it's your notebook, it's your notes. It's your notes. Okay? So if you want to understand what the subject, you need to read that the recommended textbooks. You need to read them. They are meant to empower you with knowledge. So, what is angular momentum? What are we? What do we understand under angular momentum?
Okay, for me, what I understand is it's motion in angular motion, not straight.
You're still broad. I'm very focused on one thing.
I'm trying to
focus on
my
question is focusing on the particular. What is angular momentum? Okay. I've realized that if I stop talking, nobody talks. So I'll find ways of getting you to talk. So, there are 4 quantum numbers, you know. Remember, we're talking about quantum theory now. Okay? Or quantum mechanics. There are 4 quantum numbers, you know. Which are those?
Spin,
Yeah.
Principal quantum number,
Yes.
and angular quantum number. And the other one,
Angular what? Angular
magnetic
momentum quantum number. And then
the other one, I forgot.
magnetic.
Magnetic, yeah.
Angular momentum quantum number. So that quantum number must be related to what we're talking about. Angular momentum. Angular momentum is a property. In fact, it's a property you associate with rotational motion. It's a property you associate with rotational motion. And in quantum mechanics, or let me put it this way, when you solve your Schrodinger equation, for the hydrogen atom, the simplest. I mean, that one is known. It's been done. The results are known. So when you do that, you discover the following: that there is a set of equations known as spherical harmonics. In those equations, you find this angular momentum quantum number. In fact, put differently, spherical harmonics are just mathematical equations, set of mathematical equations that do other stuff. But upon trying to find solutions for the Schrodinger equation, it was discovered that they work. They work. In fact, they speak a language that is very surprising. In there, you find the angular momentum quantum number and the magnetic quantum number. They are there. Spin is there. The principal quantum number is there. In fact, those equations, they explain the existence of the periodic table of elements. What they say is that behind the periodic table of elements is mathematics and nothing else. That's the entire periodic table is based on mathematics. So it's a mathematical construct. Periodic table is a mathematical construct. So you can imagine how much work has been done trying to solve this Schrodinger equation. That mathematicians, or let me say physicists, realize that spherical harmonics do give results, understandable results, and the angular momentum appears there. In fact, it appears as a parameter. It's until you understand the relationship between this solution and the atomic structure that you realize that this that you think is just a parameter is actually angular momentum. That is the way you begin to realize that actually the periodic table of elements is based on mathematics and nothing else. So there's nothing that is accidental. There's nothing accidental in the periodic table. It's all mathematics. So and therefore you expect that the behavior of atoms, atomic behavior, and everything that has got to do with the periodic table must obey mathematics, and it does. And it does. That is why it's important for chemists, especially physical chemists, to have some reasonable background of mathematics. It's not because somebody is just trying to make life difficult for you. In order to understand physical chemistry at large, you need a relatively good background in mathematics. In fact, my feeling as a student was that there is too little mathematics that is infused into chemistry. That's one thing that always frustrated me. So I bought myself many mathematical books in mathematics, always looking for one that makes things simple for me to understand. Bought myself lots and lots of books in physics that explain things to me that I don't have explained in chemistry, because chemistry is about, basically it's about the periodic table. If you understand how atoms and molecules behave on the surface, you are good. But often as a chemist, you need to go deeper and find the reasons why, or even be able to predict what's going to happen. Because if you don't understand what lies underneath, in fact, then you cannot do any research, you cannot do any further discoveries. You simply appreciate what's on the surface, but not understand what lies underneath. So this is the interesting stuff that comes out of mathematics. The solutions to the Schrödinger equation, and especially angular momentum. So angular momentum is, so how you explain it is left up to you. You just make some reading. Just make some reading. The reason why I don't like giving straight answers at honors is because I've realized that students then sit back and don't read. They just take what I've said as the answer. And then when I ask a question, just give me back what I've said. But what I expect is that you demonstrate understanding or the willingness to know more. It's always impressive. I mean, as a teacher, I always feel good about reading something from a student who demonstrates that they have read further. Any teacher loves that, to see a student demonstrating that they have read. They are not stereotyped to what is said by the individual. In fact, that is why you have so many books written, because we all have different, we see science from a different point of view. So one book is not the same as another. So the books that the recommended textbooks or the textbooks that are recommended to you, they are meant to give you different perspective. That is how you learn science. Hearing from from different people saying the same thing. It gives you a picture, a multi-dimensional picture. So, frontier orbitals. What are we talking about? When we talk about frontier orbitals, what is it we're talking about? Before you answer, often when I ask questions here, I expect you also to demonstrate that you understand inorganic chemistry, that you understand organic chemistry. So now you can answer. What are we talking about if we talk about frontier orbitals?
The orbitals that are involved in the interaction of the atoms or molecules, like the LUMO and the HOMO orbitals.
Can you explain what those are?
The highest unoccupied molecular orbital, the one without any electrons occupying that orbital, those orbitals. The lowest occupied molecular orbital is the one that I'm not sure. The orbital that has electrons, that is occupied by electrons.
Okay, let me put it this way. Frontier orbitals is the terminology that refers to a type of orbitals that we encounter in conjugated hydrocarbons. If you draw a molecular orbital energy level, like you draw them in inorganic chemistry,
yeah.
you drew them at third year.
Yeah.
So you can draw molecular orbital energy levels also for hydrocarbons, especially the conjugated ones, starting from methane right upward. Now, once you have that picture, you've got on the side your free atoms. In the middle you have your molecular orbitals. You remember that molecular orbitals are given a different designation than the atoms. Yeah. That is what I would like you to show in your assignments, for example, that you know that. If you go, did I write it down here? Molecular orbital energy levels. If you, no, I did not write it here. If you look at the atomic molecules, you have them in your textbook. You have got molecular orbitals, molecular orbital energy levels there. Atkins has put also the symbols that are used for this to designate those molecular orbitals. So if you write, for instance, the electron configuration of that molecule, those are the symbols you use, not the atomic. Those are irrelevant now. Those are irrelevant. So you use the molecular, the symbols that are used to designate the molecular orbitals. So, and then you attach the electrons. Okay? Build-up principle. So we start putting electrons in those energy levels because they are of different energy. That's why we call them we call the diagram molecular orbital energy level. They have different energy. Okay? So, you occupy each orbital with at most 2 electrons with opposite spin.
Dr. Dladla?
Now, yes.
Hello?
Yes,
Dr. Dladla?
I'm listening.
Okay, we can't see what you're writing.
I'm not writing at all, I'm talking.
Okay, because then I thought that maybe you're writing something.
No, I'm just talking, but can you catch every word I'm saying?
Yes, we can hear what you're saying, just that we thought that maybe you're writing something.
No, when I start writing, you'll see it.
All right, thanks.
So, and then we fill in the electrons. Fill in the electrons. So it means you must be able to draw a molecular orbital energy diagram for a conjugated hydrocarbon. That's what, in fact, that is when when you begin to describe bonding using pi electrons. There is an approximation method called the Yueqin Method. So you must be able to draw those molecular orbital energy diagrams. That is why I'm saying that you cannot see physical chemistry in isolation, because you have drawn those diagrams in organic chemistry. Organic chemistry even inorganic chemistry cannot do without drawing those diagrams. So you have to, and that you did at third year. You should have been able to do that at third year. So at honors, that is child's play. So you should be able to draw those. Now, you come to a point upon filling your electrons, you run out of electrons. So, and that orbital that has got the last pair of electrons, you call it the highest occupied molecular orbital, HOMO, HOMO, highest occupied molecular orbital. The one above it, therefore, is empty, and everything above is empty. So, the one above this occupied one is called the lowest unoccupied molecular orbital, LUMO. Because of the energy, you're talking about energy, that's what you're saying. That's what you're saying. The lowest unoccupied molecular orbital has got higher energy than the highest occupied molecular orbital. And this plays a role now when you start exciting those electrons. And they make a transition between these two. Because the transition, depending on the properties of the molecule, can be to any of the above lying. Okay? To any. So, the energy that you require in order to make that excitation to the above unoccupied molecular orbital corresponds to the energy separation. It tells you that frequency tells you what is the difference between the two. What is the difference between the two? And what will happen is that when that electron, the excited electron falls back, it emits energy. When it emits that energy, Now, what will happen is that it's either you can see color or you don't see color. If you see color, if that energy that is emitted issues color, it means, what does it mean? What does it mean? It means the energy separation lies within the visible range. It lies within the visible range. So now, when you don't see color, what is likely the reason? About this energy now, the energy separation.
It could be ultraviolet.
What does that mean, ultraviolet?
It means beyond
Beyond the
It means the energy is large. It means the energy has become large.
It could also be infrared.
Infrared cannot be. What happens in infrared?
I know the energy is lower.
What do molecules do in infrared?
vibrate.
They vibrate. They vibrate. But what visible color is associated is closer to the infrared?
Red.
It's red. It's red. Okay. So if you see red, you must immediately think it's the other end of the spectrum of the visible range of the spectrum. The smaller where you've got the smallest of energies. Where you've got the smallest of energies, which means the frequency there is long. In fact, it means the wavelength is long. Okay, the frequency is small because the energy separations are small, but the wavelength is long. This is the same color that you see in the afternoons. In the afternoons, when you look at the sun, it takes a red tinge. This is simply because the wavelength, the size of the particles, dust that rises from the ground into the atmosphere, has got reflects that range of light from the sun. So the color tells you what is the size of the particles that are being impacted upon by light rays. So when you've got blue, when the sky is blue, the sky it tells you that the molecules in the sky, they particularly reflect blue light. They particularly reflect blue light, and you can trace that back into the molecules that are present in the atmosphere. So now, what I want to say to you is that frontier orbitals, they impact, I mean, all the life you see around you. All the color that you see, is because what goes into your eyes comes from the visible range. You don't see anything that is outside the visible range. You don't see anything that is outside the visible range. So it means if you don't see the water molecules in front of you, it's simply because the wavelength that is reflected into your eyes is outside the visible range. You cannot see it. It doesn't mean they are not there. So all you see is within. So you can see how limited the human vision is. You see? Very limited. Very limited. There is lots and lots of stuff out there or in our vicinity that we don't see. But it's just there. But it's just there. It's just because we have this limited instrument for vision. So, any questions so far? Now, probably question 2 must have been easy, isn't it? Must have been easy. So we can go to question 3. Question 3, we have already talked about this. What is this about?
Photoelectric.
Photoelectric effect. Go and look at photoelectric effect. And don't say I didn't say it. There are tasks, a range of tasks at the back of the text of each chapter. Go and attempt those. If you feel you're running out of tasks to work on, contact me. I'll give you some. Now, consider question 4. Consider a particle in a one-dimensional box of length L and calculate the percentage change in the lowest energy level upon 10% increase in length. So, you know the equation for calculating such energy, isn't it? We are looking at a particle that is running along a string. This is confined to a string. That's why it's just in one direction. It can only move in one direction, to and fro. On a single string, imagine a cotton string. You can only move in that direction. Okay? So, and we call it a box because we limit the particle. We raise at both ends. At both ends, we raise the potential to infinity. So the electron cannot go there. So it's free only within this box. Okay, it can move about only in this box. See? So the energy, you can write and then we solve the Schrödinger equation. Then we solve the Schrödinger equation using and get an expression for energy. Now, the question here is, calculate the percent change. Percent change. What does percent change mean? Percent out of 100. Percent is out of 100. So, percent change in lowest energy level. So, we're looking at the lowest energy level, that is n equal to 1. What we do is we increase the length of the box by 10%. Increase the length of the box by 10%. So let me see if I wrote it down. This thing. I see. I think it's set here now. Come on. So this is the equation we have. Oh, what's this now? All right. So, remember this. This is the equation we wrote for energy. But remember, when you write this equation, you cannot write it without this. Because that instructs how much energy is in there, which level you're talking about. So if you write this alone, it suggests that you don't know what you're talking about. Because that alone does not tell us what energy level you're talking about. Okay? So, we are looking at that quantity here, L. So, now, if we increase L, what do we expect will happen to the energy?
Decrease.
It will decrease.
It will decrease. It will decrease. So, this here is the same as E final minus E initial. So, we increase the length by 10%, which means 0.1 times L plus L. So, once we've resolved this, we take, so we're resolving this, and we take this whole thing outside. So, your expectation is confirmed. There is a decrease of how much? What?
17%.
17%, exactly. There's a decrease of 17%. In other words, what this is saying is that as you are writing, you already expect something. And it should surprise you if it doesn't happen. If you get something else. If you get a plus, for instance, there, it should surprise you. What is this? You see? So, that is if you read with understanding. This is what I'm saying. You need to read with understanding. You need to expect something. So, further, the next question says, calculate the percentage change in the difference between the lowest and the adjacent upper level when the mass of the particle is increased. That should be past tense. Increased. There's an error there of tense. Don't think I don't have command of my tenses. Increased by a factor of 2,000. This is an interesting observation you will make here, because between the electron and the proton, there's exactly this factorial difference in mass. Okay? So you imagine yourself, you imagine what a proton confined to a string would be doing as compared to an electron confined to a string. That's what we're saying actually. Okay? So, if we go now from an electron to a proton, by how much does the energy change? So we're talking about the following. We're talking about energy level. So I'm writing now, can you see that? Yeah. Good.
Yes, it's written more.
So I also expect questions. So we're talking about this difference here. That's the question. By how much does it change? So it means we must know first how large it is initially, in order to be, and how large it is at the end, in order to talk about the difference. Okay? So what we do is the following. We look at this. In fact, I had to come myself because I didn't want you to see the answer first. But it doesn't matter, because when I ask you to do it, I will tell myself, I've shown you. So, the difference, first, this is the difference we're talking about. That's a general equation, isn't it? We can use that equation for any adjacent energy levels, any two adjacent levels. And it simplifies to this. Is it clear why it does this? Please talk. If you don't understand, say, I don't understand. Because, I mean, if you keep quiet, I will just go on. But next time you meet this in the exam, it's a different issue. Because you'll be alone there. The next person will be a few steps away from you. So, that is the general expression you use for the energy difference between adjacent energy levels in a one-dimensional box, or particularly in a one-dimensional box, confined to move along a single dimension. So, what does this mean? We can, in our case, we're talking about n equals 1, because it gives immediately the difference between n and 2, isn't it? But our equation can be used again for any other difference. We could have put, if we wanted between 3 and 4, for n we would put 3. That is the lowest energy level. Because the adjacent upper energy level comes then from the equation itself. Okay? So, now, all we need to do now is to put the, or let me say first, we have, let's take the electron. We put the mass of the electron. We could have put 1 there. We could have put 1 because a factor of 2000. We simply multiply m by 2000. See? I say we could have used the electron because the mass of the proton is about this. This is the factor between the two. So 2000 is just an approximation. So that factor is about closer. It's closer to the factor between the two masses, electron and proton. So, but the information we get out of it is the same. So, Now, we want to see what the difference is, the change in difference. In other words, what we want to see is this. Do you agree? The change in difference. So it's delta delta E, which means we have delta final minus delta E initial. Okay? Divided by delta E initial. So we start with if we start with m equals to 1, so we just write m there, and this is what we have. Okay? Yes.
Why couldn't we use the same principle for the first one?
What do you mean for the first one?
Delta final minus initial over initial. Why couldn't we apply the same thing for the first one? The first one you just said delta minus delta initial.
This here refers to that.
Okay.
Do you get me?
Mm-hmm.
Don't say yes if you don't understand.
I get you.
This here,
energy from.
this is the difference.
Yes, I hear you.
It comes from here.
It's partial fractions. It's sort of like partial fractions, right? Yes, sort of.
Well.
So what I'm asking is, why do we use partial fractions?
It looks like a second derivative. I wouldn't say partial fraction. It looks like a second derivative.
Okay.
Do you see that? It's a second derivative. Because it's a change of change. Now, remember that we've already calculated the change here. I mean, we already have the equation that gives us the change here. That gives us this here. Isn't it? So what we are asking ourselves now is, how does that change? In fact, the first question was about just this energy level, and we found that this is minus 17%, isn't it? Now we ask. Now this is B. This was A, isn't it? Yes. Now, this here is a change. This is a change. This is a change. This is the change you have in brackets there. So if you change now, so this is the change before anything happens. Delta E. This here is this before anything happens. Do you get me? Be sure you understand what I'm saying.
I do, but yeah, I hear you.
If you say I hear you,
so if it was N3, it was N1, N2, and N3.
You remember, we're looking at adjacent energy levels.
No, I'm just saying in a different scenario.
So in a different scenario, let's take N2 and 3. You have got this, you've got this. So this is.
No, I'm saying, what if they say we consider all three of them, N1 and N2 and N3? Oh, we can't.
Let us start with the simpler one. Let's start with the simpler one first. Okay. Because we are interested in adjacent energy levels. Let us see what happens there before we can. Let's not put too much on our plate.
oxygen. I'm not a trader. So if it was, how would you express the equation?
Okay, let me put it this way. As n tends to infinity, you will realize that this becomes very small. Very, very small. In fact, that is what leads to us thinking that energy is a continuity.
Okay.
You see? The difference between N1 and N2 is different from the difference between N2 and N3. You see? So we are mixing two different things. And this difference changes as you go up. Mainly because your energies, these energy levels here, they become large. So at some stage, the difference between this difference here you have here is very small. You've got the big number this side, you've got a big number this side, and the difference between two is very small. Okay? And you are looking at this difference, at the change of the difference, at the change of the differences as you go up. So these changes, I mean, what is at the bottom? What is at the bottom becomes, or let me say, this whole quotient, what you have here becomes very little, so that the jump from one energy level to the next is, in fact, it's even smaller. It's smaller than kT. Smaller than kT. kT is the mass we use usually to measure the difference in the energy levels. Because if we say the kinetic energy of oxygen in this room is already at very high quantum numbers, principal quantum numbers, it's because the difference in the energy levels is very small compared to kT. The temperature is 298. In fact, we've got more than 298 here, which is we've got about 25, isn't it? 25 degrees Celsius, which is we've got just about 298 Kelvin. So times the Boltzmann constant, that value is a lot of energy already at room temperature, which means molecules are able to jump many energy levels. Only when this jump reaches a level where the energy difference is large, do molecules come to cycle there, because the energy they have does not allow them to jump between energy levels. So kT, if you ask yourself about which energy levels could an oxygen, let's say a helium atom, occupy at these temperatures, this is what you encounter. You look at kT. How large is kT? It's the way of approximating the energy you have, because kT tells you how much energy is available at all. And then you look at the difference, at the energy differences that are available, and you compare the two. Okay? As long as, if kT is larger than this energy level, the separation, it means the molecule is already above that. But as soon as the kT is smaller than this energy level, it means the molecule needs extra energy, okay, in order to overcome the separation. So, what I'm saying is that Let us look at how this difference changes first. Because that is what we want to look at. We're comparing, like I say, we're comparing an atom and an electron, the behavior of the two. Okay? We want to see what happens if we go from an electron to a proton, because this change here will allow us to do that. But if I write a denominator there, I should write a denominator there. I included it here because we are interested in percentage. Okay? But if I simply consider this here, it's just a difference of a difference, nothing else. Okay? But if I decide to divide on one end, on one side of the equation, then I must also divide on that side. Then it becomes the same thing on both sides. So, this is the initial separation we start with, which is given here. And then we change. If we change the mass now, we're changing the mass. So we are still changing in the denominator. This time, however, we're changing the mass, which is not squared. So we will end up with this being 8 times 2000 m L squared. Okay? So it means final, delta E final here, in this difference here. If we write this difference, we use this equation. For M, we write, let me remove that. For M, this is what we write. So, the reason why I write M there is in order to say that there is a factor of 1 there.
The
but there
meeting
is a
has
factor
been
of 2.
automatically extended.
There is a factor of 2000. So, this equation belongs there with this mass, and there you have the same equation as that, divided by the same. So, I calculated this. I sat down and calculated it and found that if you change, that this separation here will change by 99.9, in fact it will decrease. Is it reasonable that it decreases? That's the question. Is it reasonable that it decreases? If you take this equation here and you increase the mass by 2000,
Yes.
it must decrease. So the decrease is reasonable, isn't it? It's reasonable. But look at how much it is. The decrease. So it means for electrons, the energy separation is large, but for protons, it's very small. For protons, it's very small. If you make this transition from an electron to a proton, that separation is very small. That's the conclusion we get from this whole exercise. It's the conclusion I wanted you to get. Now, are there any questions? Let me see. Why am I getting this message? We're supposed to be here until 4. So why are we getting this message? But anyway, any questions before we proceed? Before we proceed. Just to repeat what I said when we started. Question 9 and 10, I'll do on discussion forum. That is my way of twisting your arm. Because you have to get to the discussion forum. You'll be surprised as soon as you get there. As soon as the conversation begins, you'll be able to ask many questions you are not asking right now. Because, I mean, there is nothing that stops you as an individual to pose a question there. Absolutely nothing. Whether you work or you don't. You can pose a question and leave it there. I'll answer it. And posing a question also does not mean you are dumb or something like that. It means you are inquisitive. This is what I want to see in students. Curiosity. Don't believe people say curiosity killed a cat. Nothing like that. Curiosity makes a scientist. All scientists, all big scientists are very curious people. Highly curious people. So, I would like us to start with question 6. Let's start with question 6. Now, I wrote these sections here so as to guide you. You can go at your own leisure, go and read those sections. So, the question we have here is identify